In this video, we're going to pick up where we left off in section 7.2. So let's finish this last example for the disk method. So we want to find the volume of the solid formed by revolving the region bounded by the graphs of f of x equals 2 minus x squared, g of x equals 1, about the line y equals 1. So first let's draw this graph. So the graph of f of x equals 2 minus x squared, that minus sign means I'm flipped upside down parabola. The 2 means I shifted up 2. So it's going to look like this. Right? This is my f of x equals 2 minus x squared. And then my function that is g of x equals to 1. That means a horizontal line at the y value 1. And that's also the line y equals to 1. So that green line there is also going to be the line that we revolve around. Right? So let's go ahead and highlight what our area is that we want to revolve. That's this area that's bounded by g of x equals to 1 and f of x. And we're going to revolve it about that line y equals 1. Okay. So as before, we need to determine two things. We need to determine where we start and finish, right? Those points that I marked there. And then we need to determine our radius. Right? So first, let's find those points of intersection. So in order to do that, we need to figure out when 2 minus x squared equals to 1. Right? Because when f of x equals to g of x. So we add x squared, we subtract 2. We get 0 is equal to x squared minus 1, which factors to be x plus 1, x minus 1, when I get x equals to negative 1 and x equals to 1. So that's where we start and where we finish. So now we need to determine the radius. Okay, so to determine the radius let's go ahead and draw the rectangle we want, right? The rectangles look like this, and we know that we have a delta x here as the width, and now we want to find the height, right? This height right here is our radius function. In the previous example, our radius function was just exactly equal to our function, like here would have been like 2 minus x squared. But that would be if we were revolving around the x-axis. In this case, we're not, right? We don't want 2 minus x squared is this whole part right there. We don't want that. We don't want that whole part. We just want the piece from the green line to the purple line. So how are we going to find that? The piece from the green line to the purple line is the piece from the black line, the x-axis to the purple line, which is 2 minus x squared, right? That's our function. And then if we subtract this little piece down here, which is 1, then that will give us that pink spot that I have highlighted there. Right, so let me try highlighting that again. I apologize. So this is our area that we're interested in. In order to find that r of x, which is right here, that height, well, what do? We take the full height, which is from here to here, and we subtract the little piece, which is right here. So the full height is this spot right here, and then the little height is the minus 1, and that gives us the pink for a total. Okay, so that's our radius function. We should simplify that. Our radius function is going to be 1 minus x squared. So now we're ready to go. We have our radius, we have our points of our beginning and end. So the volume is equal to pi times the integral from a to b of r of x squared dx. So it's pi, we start at negative 1, we go to 1 of 1 minus x squared, quantity squared, dx. Remember, 1 minus x squared is 1 minus x squared times itself. So we need to expand that binomial. There's a fast way to do it if you remember that it's the first one squared, 2 times the first times the second one, and the second one squared. So what I mean is I can do this really fast. I say, okay, 1 squared is 1. 2 times 1 times negative x squared gives me negative 2x squared. and then negative x squared gives me positive x to the fourth. So I can really quickly expand out that binomial. If that didn't make sense to you, just go ahead and multiply it out just like I did there. Now it just comes a matter of a integral problem, and I'll let you do that on your own, and it ends up being 16 pi over 15. Great. Okay, so now let's take a look at the washer method. All right, this is going to be a similar method to the disk method, but instead of a disk is solid, a washer is going to be more like a donut. So the disk method can be extended to cover solids of revolutions that have holes in them. Right, the disk method, it was very important that that axis of revolution was adjacent to our rectangle. But what happens if they're not, right? What if I have a solid that looks kind of like a donut? So for example here, say this is my axis of revolution, right? And now my rectangle looks like this, right? And so I'm going to take this rectangle, and once again, I'm going to revolve it around the axis of revolution to create now like a donut instead of a disk. Why is it a donut? Well, because I have this inner radius, which I'm going to call little r, and then I have this big radius, which I'll call big R. All right, I call it little and big because big R is on the outside and little r is on the inside. All right, so this is our rectangle that we're going to wrap around this axis of revolution, and as you can imagine there, it would look like a disk. Right, so again, let me try to draw a picture of here's our axis of revolution, right? And then if I were going to draw what the original rectangle looked like, it looks something like that, right? That is our original rectangle there. And so this space right here would be little r. This space up here would be big R. Right? So now let's think of what the volume of this washer is. We know in general that the volume of a cylinder is going to be pi r squared h. So now here we could think about this as finding the the volume of the outer disk, right? So the volume total will be the volume of outer disk minus the volume of inner disk, and that would give us the volume of the donut. Right? Well, what's the volume of the outer disk? Well, it's pi and then big R, because that's the radius of that one, squared times the height, which in this case I should have labeled, I apologize. In each case, we'll still keep it as W times W. And then minus, now what's the area of the little? Well, it's going to be pi, and then it's going to be now little r squared W. And now if you notice, we can factor out a pi to the right, and then I'm left with r squared minus little r squared, and I can factor out a w to the left, just so it looks like that. Right? So our volume is equal pi times the little, pi times the big radius squared minus pi times the big radius squared minus the little radius squared times w. And just like before here, if I have this solid of revolution that has a hole in it, right, and I want to find the volume of this random solid of revolution with the hole in it, well, I can put infinitely many of these little donuts in there. Infinitely many means, hey, take the integral, right? And so my volume formula ends up being for this is pi times the integral from a to b of, now it's going to be, though, the big radius function squared minus the little radius function squared dx, right? Because if I were going to take finitely many of these, I'd add up a bunch of these donuts that have this volume, right? And when I start to add them up, the summation becomes the integral, and the w, or the width, becomes the dx, right? So in an exact analysis like we had with the disks, we have with the washers, right? So in this time, this becomes like the outer radius minus the inner radius, right? Instead of just pi r squared, now it's pi big radius squared minus little radius squared. So for example here, if I had this function, say it looked like this, right? And whoops, let's try this. If I had, this was one function, say, and another function was this function right here, and I wanted to take this area that's bounded by the two of them, and I wanted to wrap it around this axis of revolution, right? And so let's just say that the start point here where they intersect, the end point there is there, and I want to revolve that. Well, this distance from the purple to the axis of revolution would be my little r of x, and this distance from the big portion, or the blue graph, would be our big R of x, right? If I were to draw this rectangle in there, right? And that's the rectangle that we would revolve around the axis of symmetry, or sorry, the axis of revolution, to give us a bunch of donuts to fill out that space. Okay, so now let's find the volume of a solid formed by revolving the region bounded by the graphs of y equals the square root of x, y equals x squared about the x-axis. So first we're going to draw this here. Y equals x squared is a parabola, so it looks like, oops, and it should, whoops, and it should touch the origin. All right, so let's say something. It'll drive me crazy, sorry guys. This would be y equals x squared, and then the square root function looks like this. So let's give it a little bit more beef here. This is y equals the square root of x. All right, so we want to take this area bounded by the two of them right here, and we want to revolve it around the x-axis, right? So what we want to do is, once again, and for this formula, what do we need? We need to find A, we need to find B, we need to find big R of x, and we need to find little r of x. All right, so let's go ahead and find big R of x and little r of x. So in order to do this, we put our little rectangle in here, because this is our rectangle that we would revolve around the x-axis in order to get our donuts. And we think, okay, how do we get the bottom part of it, right? How do we get this little radius that goes from the bottom of the rectangle to the solid there? So this little one is r of x. So what is that r of x? That r of x, the distance from the x-axis to the bottom of our rectangle there, is actually going to be y equals x squared, right? So r of x is going to be our x squared. And then now the big R of x, right? That's our radius from, that's the distance from the x-axis, or the axis of revolution, to the top of our rectangle there. The big R of x is going to be given by the square root function. Right? So now we need to figure out our points where it intersects, where we stop and finish. That one's going to be 0. And now we need to figure out this guy. So here our point of intersection. How are we going to get that? We're going to get that by setting x squared equal to radical x. Right? So I get x to the fourth equals to x. Right? So I get x to the fourth minus x equals to 0. Let's factor out an x. I get x cubed minus 1 equals to 0. So I get x equals to 0, and x equals to positive 1. So this happens here at positive 1. So now we have everything we need for the problem, right? Our volume is equal to the integral from a to b of big R of x squared minus little r of x squared dx. So this will be the integral from 0 to 1 of big R of x, which is the square root of x squared, minus little r of x squared. Little r of x is little x squared dx. So here at the integral from 0 to 1 of x minus x to the 4th dx. And now if I do that, I end up getting 3 pi. Oops, and I forgot pi, didn't I, this whole time? Let me try that again. So this volume, remember, we have to have pi in there. Volume equals to pi times that integral. Right, so I forgot it every time. So let's fix that. Pi. So now our final answer is 3 pi over 10. If we were to multiply out that integral. Okay, so in each example that we've seen so far, right, those two pictures we see there, and in the earlier notes, all of our axis of revolution have been horizontal, but it is possible to have a vertical axis of revolution. If we have a vertical axis of revolution, then we should integrate with respect to y. All right, so let's go ahead and look at this example here. So here we have, we want to find the volume of the solid form by revolving the region bounded by the graphs of y equals x squared plus 1, y equals to 0, x equals to 0, and x equals to 1 about the y-axis. So y equals to 0 is going to be the y-axis, or I'm sorry, y equals to 0 would be the x-axis. X equals to 0 would be the y-axis. And then the line x equals to 1, right? That's a vertical line. Okay, so let's go ahead and graph what this would look like here. Okay, so I've got this. Let's graph x squared plus 1. X squared plus 1 is a parabola shifted up 1. All right, so it looks something like this. Now we want y equals to 0, which is the x-axis. So that's down here. And then x equals 0, which is the y-axis. And then the line x equals to 1. So the line x equals to 1 would be at the x value 1 here, we draw a vertical line. All right, so this is x equals to 1. So we want to take this solid here. So let's fill in. Remember, it's a solid bounded by y equals x squared plus 1, x equals to 1, the y-axis and the x-axis, right? So this is our piece right here of area, and we want to revolve that around the y-axis. All right, so in order to revolve it around the y-axis, I need to rewrite my equations, or my equation, I guess there's only one, in terms of y. All right, so our equation is y equals x squared plus 1. So I get y minus 1 is equal to x squared. So that means that the square root plus or minus the square root of y minus 1 is equal to x. But notice here that we are on the right side of the y-axis, right? So we only need the plus, right? So in other words, our equation becomes x is equal to the positive square root of y minus 1. This part right here is the negative square root of y minus 1. This part right here is the positive square root of y minus 1, right? Okay, so what are we going to do here? Now we need to determine, just like before, if we need to find our inner radius or outer radius, what's going on here. Okay, so we're revolving it around the y-axis. So I actually like to turn my paper over and look at it like this is the top and this is the bottom. So notice something strange happens right about here. Let me draw that a little bit straighter. right? Because in this piece, for this part right here, my top function is x equals to 1. My bottom function is the square root of y minus 1. But then over here, my top function is 1 and my bottom function is just the y-axis, right? So some strange shift happens right at that point. And what is this point right here? That something strange happens. Maybe I should mark it with red since it's like a kind of a point of intersection. We know that this is the y value 1. Why? Because my function was x squared plus 1, which means I shifted up 1. So this was the y value 1 here. Right? So now, when I go to do this, I have two separate pieces of my intervals to do. I have this little piece and this little piece. And on those different intervals of y values, I get different top and bottom functions. So this actually ends up being two different integrals. So let me show you what I mean. On the interval, and I'm going to put in parentheses of y values, because remember, everything's in terms of y in this case. Let's go from 0 to 1, right? That's what I'm talking about, this piece right here. On that interval, what's my top function? My top function, if I flip my paper over, is x equals to 1. So 1. And my bottom function is just the y-axis, which is x equals to 0. Right? And that, you could think of it, it's kind of like the disk method here, right? This is my rectangle that I'm looking at. Now, on the interval, again, of y values, from, let's see, from 1 to, I should find this value. I never found it, right? Where we stop up here. Right? So where we stop, this is our point of intersection, because that's the y value where we stop, right? I never actually found that value. So how do I find that value? Well, what do I do here is I set y equals, or actually I want the y value, so I set the square root of y minus 1 equal to, even better. What is the x value where that happens? The x value where that point that I just marked it happens at x equals to 1. So I can go to my function here that's y equals x squared plus 1, and I know at x equals to 1, this becomes y equals 1 squared plus 1, so y equals to 2. So I know right here is the y value 2, because I know the x value that I'm plugging in there is going to be 1, so the y value that corresponds to that on the graph of y equals x squared plus 1 is 2, right? Okay, so that's how I know here that I'm going now the y value from starting at y equals 1 to y equals to 2. So now during that function, this is where I have my other rectangles, right? So again, I'm wrapping it around. So this is my little r of x, and now this is my big r of x. Sorry, things are getting a little bit messy in there, right? So my top function, or I guess I shouldn't call these top and bottom. I apologize. I should call it big r of x and little r of x. So this means big r of x because it was the top, and this means little r of x because it was the bottom. I apologize. I was getting used to the area formulas. So instead of saying top function, let's say what's my big radius? Well, my big radius, again, we've marked, is going to be from 0 to 1. It's going to be that blue line there. So it's going to be 1. And now my little radius is given by the purple, right? And the purple is going to be the square root of y minus 1, right? So if I want to find the total volume, it's going to be the volume of the first part. So we'll call it volume 1 plus volume 2, right? The first part being the part where, like this part right here, and the second part being this part right here, right? Okay, so now I do the integral from, the first part's going to be from 0 to 1. I forgot pi again, didn't I? Pi from 0 to 1 of my big radius, which we said was 1 squared, minus my little radius, which is 0 squared, dy, plus pi times the integral from 1 to 2, because those are the y values. And then now I'm going to have my outer radius, which my outer radius we said was 1 squared, minus my inner radius, which is the square root of y minus 1 quantity squared dy. So this is pi, the integral from 0 to 1. This just ends up being 1 on the inside, so dy plus pi, the integral from 1 to 2 of 1 minus, careful here, when I square this y squared, I still need to keep the minus parenthesis. Right, so here's what I mean. I'm going to put a bracket here. So when I square the y squared, these cancel out, but I still have the parenthesis. I still need to distribute that negative sign. Right? So this becomes the integral from 0 to 1 dy plus pi, the integral from 1 to 2 of, that's going to be plus 2. So we get 1 plus 1, so it'll be 2 minus y dy. And when I compute that, my final answer is going to be 3 pi over 2. I'm going to go erase this right here just because it's a little bit messy. Okay, so once again, I have some relevant textbook exercises if you don't think that you have enough practice with the homework. Thank you so much.